Okay, this is a new situation. We'll have a linear charge density on this problem, but this one doesn't extend to the left side, so we'll have to do a little monkeying to figure it out. But we have an alpha particle at point P, and an alpha particle has a charge of plus 2e and a mass of that much there. Alpha particles were discovered in the late 1800s in the early studies of radioactivity, and at first all they knew were that they were a particle with mass and a positive charge. They didn't know much about them, so they just called them alpha particles. Ernest Rutherford, who discovered the nucleus of the atom, also later discovered that alpha particles were the nuclei of helium atoms. And it turns out what an alpha particle is a little bundle of 2 protons and 2 neutrons. We still call them alpha particles. They're still a byproduct of radioactive decay, and it's the radioactive decay of things in the interior of the Earth that produce the helium that we have on Earth. Those alpha particles coming off of there are not radioactive. They're a stable nucleus. They pick up electrons and become helium atoms and then percolate their way upward from the interior of the Earth, and they get trapped in the same deposits that natural gas is trapped in. So anyway, that's what's going on. All right, well, we've done an example where we determined the electric field of a line of charge before when we were a distance off the axis. This was the situation that we dealt with before. This time we've got something a little bit different, and but it's still a line of charge. So I'm just going to call this distance that we are away from the axis of the line of charge d, as we had in the previous problem. And so we'll see how that works out. And in that previous problem, we found the y and the x components of the electric field depending on the charge per unit length of the charged insulator. And so we can reuse these expressions. Now in this situation, the one we're dealing with here, both the beginning and the ending of the rod are to the right of the point P. And so we may have to do a little bit of experimentation, but I'll show you how we can do that. One is, as far as we'll start off by looking at a few different situations, and one of the situations is just this one here, where we'll have a charged rod extend from a point just above the point P we're interested in off to the right. And so we'd have a little right angle here. This is the distance d that I labeled before, and I'm just going to call this situation A. I think I'll call this situation B, and this situation C. So we've got all of these that we're going to consider. A and B are going to be very similar. I'm going to call this length here L sub A. I'll call this little length here L sub B, and so that'll be the 3.54 centimeters. And then L sub C will be 11.13 centimeters minus 3.54. So this will be L sub C here. Now, I can actually get the electric field for situations A and B just by looking at the results that I had before. And if we consider, let's see, this drawing here was the situation that I figured out the electric fields for before. If I let x2 equal 0, it'll be the situation where I have something extending off to the right. And so if x2 is equal to 0, then in this situation, E sub y will equal k sub e lambda over d. I'm reusing the d. x2 is 0, but x1 is not. So I'll have x1 over the square root of x1 squared plus d squared. And the second term will vanish. If x2 is 0, there's no contribution from this thing. And so that's my expression for e sub y. For e sub x, it's not quite so nice, but it's not far off. E sub x, if x2 is 0, this term doesn't vanish because it's got a 1 in the numerator, but I'll end up with k sub e lambda times, I'll have 1 divided by the square root of d squared plus x1 squared minus, now this term, if x2 is 0, I'll have 1 over the square root of d squared, which is just 1 over d. So that's what I'll have. And these two expressions are the situation that we have in one of the drawings that I did back here. Both B and A are that particular situation, those electric fields. And so I can write down both of those for this situation. For A, it would be the y component of the electric field is going to equal k sub e lambda divided by d. Okay, we're good on that. And then the length of the rod is not x1 in this situation, it's L sub a. So I'll have L sub a divided by the square root of L sub a squared plus d squared. And there's my y component of the electric field. The x component here will equal k sub e lambda, and I'm just copying it off here but changing x1 to L sub a. So 1 over the square root of d squared plus L sub a squared. Sometimes a useful skill is just translating formulas from one set of variables to another, minus 1 over d. Okay, so that's the x and the y components of that one. Now, down here, I'll have exactly the same expressions, except instead of L sub a, I will have L sub b in each of them. And so for part B, I'll have e sub y is equal to k sub e lambda divided by d times, I just changed my L sub a's to L sub b's. L sub b over the square root of L sub b squared plus d squared. And then e sub x, do the same thing. K sub e lambda over d. And let's see, 1 over the square root of d squared plus L sub b squared minus 1 over d. So there's my x component of the electric field in this case. All right, well, guess what? The electric field of situation B plus the electric field of situation C will equal the electric field of situation A. Okay, situation A is just adding together these two charge distributions, and electric fields are additive. That's the superposition of forces, and so we'll have that. So what that means is E due to situation A is going to equal the electric field of situation B plus the electric field of situation A, and it's the electric field of, whoops, made a mistake here, one of these was supposed to have a C on it. There we go. It's the electric field of situation C that I want to know, so it's just going to equal E sub A minus E sub B. And I can do it component by component. So I'll try to keep those things in view as I'm doing this, but EC will equal, let's see, it'll be EA minus EB. So here's A. I'll do the X component first. It'll be K sub E lambda. And I know I'm putting the parentheses in the wrong place, but that won't hurt. 1 over the square root of D squared plus L sub A squared minus 1 over D minus K sub E lambda. And I'm doing the X components first. Oops, this one should not have had a D on the bottom. Yeah, that one doesn't have a D on the bottom. Anyway, let's see, 1 over D squared plus L sub B squared, the square root of that, minus 1 over D. And that's the I hat component. Okay. And then I'll also have a J hat component plus the E sub Y is going to equal, that's K sub E lambda divided by D times this thing, L sub A divided by the square root of L sub A squared plus D squared minus, this one's a simpler expression, L sub B divided by the square root of L sub B squared plus D squared. And that's in the J hat direction. So, still kind of a complicated expression. This'll work out. I think I've got stuff that'll drop out on me. It ends up being E sub C. This will give us a nice expression for the electric field. We'll have to plug in the numbers to figure this out, but that's all right. K sub E lambda over A, or K sub E lambda I can pull out. And I will have, when I subtract this from this, there's a minus 1 over D minus a negative 1 over D, which is like minus 1 over D plus 1 over D. Those drop out. And I'm left with 1 over the square root of D squared plus L sub A squared minus 1 over the square root of D squared plus L sub B squared. And there's my I hat term. And the J hat term I already had pretty well simplified, but it is plus K sub E lambda divided by D, and then L sub A over the square root of L sub A squared plus D squared minus L sub B, running out of room, divided by the square root of L sub B squared plus D squared. And that's the J hat component. So it got a little crowded over there. But those are nice expressions. Now, I earlier calculated what those values happen to be. L sub B squared plus D squared is equal to 3.65 centimeters. And when I calculate this time, I think I'm going to convert everything into per meters at an intermediate part. The square root of L sub A squared plus D squared, 11.16 centimeters. Okay, well, E sub c is the electric field at E. So if I plug in the numbers there, I'll do the x component by itself because it's bad enough. K sub E is the 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. Lambda is the charge per unit length on here, 7.67 times 10 to the minus 9th. And this is coulombs per meter. And then I have to multiply by the geometric part on here, which is 1 divided by the square root of d squared plus L sub a squared was 11.16. The centi means 10 to the minus 2 meters. Minus 1 divided by d squared plus L sub b squared, which is 3.65 times 10 to the minus 2 meters. And that's all I have to do for E sub x. Okay, I get E sub x is minus 1.27 times 10 to the third. Now let's track down the units. I have meters squared on top. I have a meter on the bottom here and a meter on the bottom there. So I'll have the meters squared will divide out. I've got a coulomb on top and coulomb squared on the bottom. One of those will divide out and I'll have newtons per coulomb, which is what I expect for an electric field. So that's always a little bit of a vote of confidence when you come up with the correct units. All right, let's do E sub y here. I had an expression for it there, K sub E times lambda divided by D, and I have to be careful to take care of all my units on this thing. So let's see, 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. There's the K sub E. The lambda, again, is 7.67 times 10 to the minus 9th coulombs per meter. And I divide by D on this thing. 0.87 times 10 to the minus 2 meters. This thing's going to knock me down to 2 significant figures, times the complicated geometry stuff, L sub A. L sub A is the 11.13 times 10 to the minus 2 meters. And I'm dividing by square root of L sub A squared plus L sub D squared, which is 11.16 centimeters times 10 to the minus 2 meters. These things end up being dimensionless inside here. And then minus L sub B, which was the 3.54 centimeters. Whoops, times 10 to the minus 2 meters. Although since I'm taking ratios of identical units, as long as I stayed consistent, it wouldn't matter. And the square root of L sub B squared plus D squared is 3.65 times 10 to the minus 2 meters. As far as keeping track of significant figures, I get 0.997 minus 0.969, 0.970. And I guess, I can do that in my head, 0.027. I have two significant figures left on that one, so I'll be down to 2 sig figs on the expression for this. And these are different enough that I probably kept 3 or 4 sig figs, so I bet I can keep 3 significant figures up here. Okay, let's calculate that E sub y. Okay, for E sub y, I get 2.1 times 10 squared Unit-wise, let's see, this was dimensionless. I'll have, let's see, meters squared. There's 1 over a meter there. There's another meter that I'll be dividing by. So the meters divide out and I get newtons per coulomb again, which is good. Okay, so there's my E sub x and there's my E sub y. And at that point, the E sub x is actually a lot larger. It's about 5 times the size, or maybe 6 times the size of E sub y. So the electric field here is mostly going to point in the negative x direction. And I could figure out a magnitude and so forth for it, but I can also figure out the acceleration of the alpha particle. And this is something maybe we haven't done yet, but let's take a look at it. Because the electric field is the force per unit charge. The force that's on a charge is going to be QE. And so in this case, I can figure out, I know the charge, it's plus 2E, which would be 2 times 1.60 times 10 to the minus 19th coulombs. So I have that. And then let's see, the E is a little more complicated, but minus 1.27 times 10 to the 3rd newtons per coulomb in the I hat direction, plus 2.1 times 10 squared newtons per coulomb in the J hat direction. And that's the force that's acting on it. The acceleration is going to be just like Newton's second law. It'll be the force divided by the mass. In this case, this electric force will be pretty much the entire force, because the acceleration due to gravity isn't particularly large. So I could calculate these 2 components of the force, divide each of them by the mass, minus 4 this one I've got 3 sig figs on, 0.6 times 10 to the minus 16th newtons in the I hat direction, plus, oh, remember when I set up this whole problem, I had y pointing downward and x pointing to the right. So I'm still using that coordinate system. And I get plus 0.7 times 10 to the minus 17th in the J hat direction. And, whoops, and I have to divide by the mass in order to figure out the acceleration. And the mass on the sheet here, 6.64 times 10 to the minus 27th kilograms. That's just about 4 times the proton or neutron mass. Not exactly. Turns out in a nucleus, some of the mass vanishes when it forms. It goes into the binding energy of the nucleus. That's a little bit of E equals mc squared there, but 6.64 times 10 to the minus 27th kilograms. So the J hat components, the one I'm doing first, it will be 1.0 times 10 to the 10th meters per second squared in the J hat direction, and the I hat direction minus 6.11 times 10 to the 10th meters per second squared in the I hat direction. With accelerations like that, you can say that it's pretty safe to ignore gravity, because these end up being on the order of 10 to the 9th times larger than the acceleration due to gravity. So we don't have enough significant figures to worry about that. That was another relatively complicated problem, but we were able to use an expression that we'd already developed for figuring it out.